In this video, we're going to look at something called ionization energy. Ionization energy is energy that must be added to an atom in its gaseous state in order to remove an electron. So that's kind of the key with ionization energy, is that it's energy that must be added, energy that's required to remove the outermost electron from a ground state gaseous atom. So we're not talking about electrons being excited. They're in their normal energy level in the gas phase. And the deal is just that if I start adding energy, the first thing that's going to happen is that the substance goes through a series of phase changes. It might go from solid to liquid to gas. But then if I keep adding energy beyond the gaseous state, we're not talking about just exciting the electron, making it jump up an energy level or so. We're going to totally remove the electron from the outer energy level. And that would then result in a positive cation. So if you wanted to write it like a little equation, it might look like this. So let's say I have element X. Element X is in the gas phase. If I add energy, you're going to remove an electron. And so that I would be left with X plus 1 in the gas phase still, and 1 electron would be removed from the outermost energy level. Interesting. So that's kind of what ionization energy is. This here is your ionization energy. I think of it as it's energy required to form a positive ion. And obviously you have to add energy because the electron is attracted to the nucleus. And so yeah, when things are attracted to each other, like I have to physically add energy to separate them. Now the stronger that electron is attracted to the nucleus, the more energy it's going to take to remove the electron from the atom. And that's the trend that we want to look at here with ionization energy. And so Coulomb's law would state that the closer an electron is to the nucleus, the distance, if the distance between the nucleus and the electrons is smaller, you have a stronger force of attraction. Therefore, more energy required to remove the electron. Makes total sense. And so in general, smaller atoms tend to have a higher ionization energy just because of distance, that when the electron is really close to that positive nucleus, the attraction is usually stronger, and then it takes more energy to remove the electron. And so they've got this like kind of three-dimensional table, periodic table shown here. And in general, if I look at like elements going down, if I kind of look at, I don't know, like all the groups in general, but maybe like if I pick on the alkaline earth metals. Well, I know that going down a group, the atoms get bigger. The atoms get bigger going down a group because the electrons are in farther and farther energy levels. Now, beryllium has electrons distributed amongst 2 energy levels, but barium will have electrons distributed amongst 6 energy levels. So if the electrons in barium are already far from the nucleus, the attractive force is weak, and they're trying to show you here that then it's going to take less energy to remove the electron by like the little, I don't know, like tiles going down into the ground. I don't know, it's three-dimensional, kind of cool. Or they've got like this group 1 example where there's lithium, sodium, potassium, and you can see that from lithium to sodium to potassium, the atoms would get bigger going down a group because the electrons are in farther energy levels. But again, then the ionization energy decreases. It goes from 520 all the way down to like 419 in potassium. Now, I'm not going to ask you about specific measured kilojoules of ionization energy. We just want to be able to predict patterns and trends. So it kind of makes sense, right? Everything is based on Coulomb's law and the degree of attraction between the nucleus and the electron clouds. So yeah, it totally makes sense. And then if you kind of look at any of the other groups, like even the noble gases, yeah, helium, neon, argon, krypton, xenon, radon, The number in the box is the amount of energy required to remove an electron. And so, yeah, even way over in the noble gases, it decreases going down a group because the radius gets bigger. And so, yeah, and when you've got big guys on the bottom of the periodic table, the attraction is weak. It doesn't take much energy to remove an electron. Okay, so now if you go across, atoms get smaller. Typically going across a period, atoms get smaller because of the magnitude of the charge. That going across, we're not adding energy levels. We are adding electrons, but they're all going in the same energy level. If I'm going across from like lithium to neon, all of those electrons are going in the same energy level. They're all going in the second energy level. But because the nucleus keeps adding another proton, the magnitude of the positive nuclear charge, and even like the charge of the electron cloud keeps increasing, and it's like a stronger magnet. So if the attraction increases going across because I've got more protons and more electrons, and they're typically in the same energy level, well, not only does the atom get a little smaller, but the attraction gets stronger. And then it's going to take more energy to remove electrons. So if you go across a group, usually you'll find that the noble gases have the highest ionization energy. They have the smallest radius of the elements going across, which then means that they're going to take the most energy to remove electrons. Highest ionization energy. So again, everything goes back to the degree of charge. So number 14 says, to compare the trends for atomic size or atomic radius and first ionization energy. First ionization energy just means that we're just removing the first electron. We're removing one of the outermost valence electrons. Explain why these trends are related. And so maybe we would say something like, if you increase the atomic radius, if I have bigger atoms, there's a decrease in ionization energy. And in a nutshell, it's just all about attraction. So if I have a larger radius, there'd be a weaker attraction. So if there's a weaker attraction, it's going to take less energy to remove an electron. On the flip side, if the radius is small, if I have a small atomic radius, it's going to result in a high ionization energy. And that's just because having a small radius means there's a strong attraction. So if there's already a strong attraction between the positive nucleus and the negative electrons, it's going to take a lot of energy to remove the electrons. And so this might be something we would look at if we were comparing lithium to sodium to potassium. Like, okay, so they all have one valence electron, and it's easier to lose one electron than gain 7. But of those three, which one's going to require the most energy to lose an electron? And then we'd look maybe at the size of the atom. We'd look at the degree of attraction, and we'd say, well, because lithium only has electrons distributed amongst 2 energy levels, those outer electrons are going to be really strongly held to the nucleus. It's going to take more energy to do that. When you get way down on the bottom of the periodic table and the atoms are bigger, then yeah, I might still want to lose an electron in rubidium, cesium, francium. But because that electron's not being held very closely to the nucleus, it takes less energy to do that. Now, to bring things kind of full circle, think about when we looked at lithium, sodium, and potassium, and I think they maybe showed you like some rubidium and cesium in a video, that the atoms get more reactive going down a group. It has to do with all of this attraction. That, yeah, as you go down a group, the atoms get bigger, the electrons are farther from the nucleus, and the attraction gets weaker. It's really easy to lose electrons from things like rubidium, cesium, francium, those big guys down at the bottom of the periodic table. And so if they have a hard time holding on to their own electrons, and it doesn't take much energy to remove the electrons, that's what a chemical reaction is. Chemical reactions result in a change in the electron structure. Because those big guys at the bottom of the periodic table have such weak attractions for their own electrons, it's easy to lose them. It doesn't take much energy to lose electrons. And in fact, like francium and cesium are so crazy reactive. I mean, cesium has to be stored under like usually argon gas, because argon is a noble gas that's non-reactive. Otherwise, I mean, just the energy in the air is enough for cesium to immediately react. And it starts giving off electrons and causing chemical reactions to occur. It's because the ionization energy is so low. The attraction between those outer electrons and the nucleus is so low. So it's that attraction that affects so many properties. The radius, ionization energy, and then also reactivity.